is Dr. Jero, or you can call me Dr. J for short. So, on this lecture, we are going to look at electromotive force. I'll just use the abbreviation electromotive force, which is abbreviated as EMF. We'll look at internal resistance, and terminal potential difference. Just use PD for short. So we are going to look at the relationship between the EMF of a cell, its internal resistance, and the terminal potential difference. But before we look at that relationship, let us define what a cell is, or a battery. A battery is simply a device that produces a potential difference and causes charges to move. So I say a battery is simply a device that produces a potential difference, and causes the movement of charges. That is the best, or let's say the simplest definition of a battery. Now, a battery is also referred to as a source of an electromotive force, or just a source of EMF. So your battery is a source of EMF. However, the term electromotive force is not actually a force. However, it is used to describe the potential difference in volts. Having said this, let us look at the concept of internal resistance. When you say internal, it has to do with the inner parts. Internal has to do with the inner parts. And when you talk about resistance is the opposition to current flow in a conductor. So when you have a battery and you are talking about an internal resistance of that battery or a cell, it means the internal resistance is the resistance that is offered by the cell due to its chemical composition. So internal resistance is the resistance offered by the cell due to its chemical composition. That is the definition of internal resistance of a cell. Now, this internal resistance causes a drop in the output potential. The internal resistance causes a drop in the output potential, and as a result of that, we have to talk about the EMF of a cell or the EMF of a battery. Now, this EMF is actually the maximum possible potential difference that a battery can provide across its terminals. The is the maximum possible potential difference that a cell, you say that the battery, that a cell can provide across terminals, across its terminals. We can also define the EMF of a cell as the potential difference of the cell when it is not delivering any current to an external circuit. The potential difference of a cell when it is not delivering any current to an external circuit. That is another definition for the EMF of a cell. Or you can just simply say that the EMF of a cell is the voltage at zero current. So let's look at the relationship between the EMF of a cell, the internal resistance, and the terminal potential difference. So I'm going to wipe this off. Now we can use this expression to draw a relationship between the EMF of a cell, the terminal PD, and the lost potential or the potential drop of the cell. For short, let us use capital E to represent EMF. We use capital V to represent the terminal potential difference, and we use small letter v to represent the lost potential or the potential drop of the cell. So we can say that E, remember from Ohm's law that V is IR. Capital R is the load resistor or the external resistor. Stands for the resistance of the external resistor, or you can call it the load resistor. While small letter v represent the potential of the internal resistance or resistor. I is common in both terms, so we can factor it out and say the EMF is equal to this I into capital R plus small r. And so from that expression we can get to find the current using the EMF divided by the summation of the load resistor and the internal resistance. So in this our equation, R is equal to the external resistance while small letter r is equal to the internal resistance of the cell. So let's look at one or two problems on this particular topic. Assuming I have let's say the EMF of a cell, we have that the EMF of a cell is equal to, okay, we are not given, is unknown, but we have that the internal resistance R is equal to 0.3 ohm. The current is 2 ampere. Let's say our current I is 2 ampere. Then the external resistance is capital R, that's equal to 6 ohm. We are asked to find the EMF. We simply use this expression. So by using this expression, we say that the EMF is equal to I into capital R plus small r. What is the current here is 2 ampere. Capital R is 6, small r is 0.3. So this implies that our EMF is 2 times 6.3, so that our EMF is equal to 12.6 volts. It's that simple. Let's look at another example before we proceed. Now, assuming we have a question, for example, we have two cells, is a question now, two cells, they have, the two cells are rated 6 volts and 4 volts, respectively. And they have internal resistance of 3 ohm. That is, their internal resistance is 3 ohm and what? 2 ohm, respectively. And these two cells, the cells are connected in parallel. A load resistor. Well, let me just write the question down so that you follow well. Two cells of 6 volts and 4 volts with internal resistance of 3 ohm and 2 ohm, respectively, are connected in parallel we have that a load of 8 ohm is connected across the coils we should find the current through the cells. How do we handle this particular question? The cells are 2. So we can say that let E1, that's the first EMF of the first cell be 6 volts, the EMF of the second cell is 4 volts. Then we have that R1 is equal to 3 ohm, R2 is equal to 2 ohm. And our load resistor or load resistance is 8 ohm. What we are looking for is I, which is the current. So we are asked to find the current in each cell. So for the first cell, we say that E1 is equal to I1 into R plus R1. So that I1 will be equal to E1 all over R plus R1. E1 is 6 volts, capital R is 8, and the internal resistance for R1 is 3. So we have 6 over 11. That gives us I1 to be 0.545 ampere. For I2, that will be equal to E2 all over R plus R2. What is E2? That's the second EMF. It's 4 volts. Loop resistance is 8. R2 is 2. So we have 4 over 10. That leaves us with I2 to be equivalent to 0.4 ampere. So it's that simple. It's actually not difficult topic. Just understand the formula, remember the formula, and you can do exploits on this. So let me wipe this off and see if we can handle another one or two problems, then we move on. So assuming I have a cell of EMF 12 volts, internal resistance is 4 ohm, and connected to an external resistor the external resistor is R, so external resistor of resistance 2 ohm. Find I. I is the current. All we need to do, recall this formula. E is equal to I into capital R plus small r. From here, make I the subject of the expression, gives you E all over R plus R. What is the EMF? Is given as 12 volts all over. The external resistor is 2 ohm plus the internal resistor, which is 4 ohm. So we have 12 volts all over 6 ohm, so that your I is equal to 2 ampere. Now there is one remarkable thing you need to note in this equation. You can see that the unit of current is the ampere, but in solving we have voltage over ohm, so it implies that 1 ampere is equivalent to what? 1 volt per ohm. Take note of this. 1 ampere is equivalent to 1 volt per ohm. So let me take this off, and maybe we can just check the very last one on this. Now let's look at a question that says a resistance R is connected across the terminal of an electric cell of internal resistance 2 ohm, and the voltage is reduced to 3/5 of its nominal value. Find the value of R. So let's see how to get this. First and foremost, when you have an equation like this, bring out the parameters. So remember our equation, E is equal to capital V plus IR. And we are told that the voltage is reduced to 3/5 of its nominal value. The nominal value is actually the EMF, the original value of the voltage, which is the EMF. So we are told that V is equal to 3/5 of E. We should find the value of R. So how do we do that? Let's substitute this value of E, V into this expression. So E will be equal to 3/5 E plus IR. If you solve this one very well, if you expand it, your E should give you 3E plus 10I all over 5. Because arrow is to be when you solve extensively. I skipped a step here. You arrive here. So eventually when you cross multiply, you have that 5E is equal to 3E plus 10I. If you bring this one like terms together, you have 2E is equal to 10I. So in that case, your E is what? 5I. So recall that E is equal to I into R plus what? R. E is now expressed as 5I, which is equal to I into what? Capital R plus small r. Small r is 2. This I will cancel out the I on the left hand side. You're left with 5 is equal to arrow plus 2. In that case, arrow will be equal to 5 minus 2. That gives us 3 ohm. So our capital arrow is 3 ohm. So that is for this particular problem. So I'm going to end this series here. My next video, my next lecture, I'll just concentrate on Joule's law of electrical heating. Thank you. Have a nice day.